So now we're going to talk about resonance and how to read curved arrows. Resonance may seem like a little bit of a hard concept to grasp, but once you do, it's really not too bad. So all it is, resonance helps explain the inadequacy of bond line drawings. So what that means is that when you have a bond between two atoms, that is saying that there are two electrons between those two atoms and they're stuck there. They're not going to move anywhere else because they're holding those two atoms together. But in some cases, the electrons can move around and they're not stuck between those two atoms. And so obviously in a drawing, we can't see the movement of those electrons. And so that's why resonance is important, because it shows us that those electrons are delocalized, or they're not stuck in that one position, but they can spread out and move around the entire molecule. So there's always one way that the molecule is situated, meaning that the electrons that are delocalized are always going to move in the same way. It's not like the resonance drawings are three different ways. It's all one way, but it's a way that we can envision it as three different drawings and put it in our minds as one. We cannot draw electrons in more than one place at a time, and so, like I said, that's why we draw several structures and mentally meld them together. The basis behind this is molecular orbital bonding theory, and we're not going to go into all of that in this video. But if you're interested in going deeper into what resonance is and why, that is what you should start with. So here's an analogy. Over here we have a mule, and a mule is a cross between a donkey and a horse. So here, the donkey and the horse are representing the two resonance drawings that make up that mule. A mule is not any more a donkey than it is a horse, and it's not any more a horse than it is a donkey. It is a perfect melding together of the two. And so if someone were to just draw a donkey or just draw a horse, that would not accurately represent what a mule is. But if we draw both of the images, if we draw a donkey and a horse, and put these brackets around them and put the arrows between them, we know that that's saying that the actual image, or the mule, is going to be a perfect meshing together of the two. So here's an example, and right now you don't really need to know when electrons are delocalized. There will be another video on how to know when to arrow push and when to draw resonance structures, but right now I'm just going to give you some examples that do have resonance, and we're going to go through how to draw the other structures of it. So this is an allyl carbocation. An allylic or allyl means that the positive charge, or some cases it can be negative charge, is one carbon away from a doubly bonded atom. So we see here these two carbons have a double bond between them, and so the carbon over is going to be the allylic carbon. So in this case, the pi bond is what is delocalized. So it's going to be the electrons in one of the bonds of the double bond. And this is showing that its electron density can be distributed throughout the molecule. And this is because the positive charge shows that there's an empty p orbital for this carbon. Again, we're not going to go super into detail on that, but that is why you are able to push these electrons over here, because there's basically an available space for them to go. And so if I were to just draw this or just draw this one, you're not accurately showing that the electrons are moving throughout it. So we have to draw both of them and put these brackets around it and the arrow between to show that the actual molecule is a mesh between the two. So some tools for resonance structures. You have an arrow, and that is going to show where the electrons are going to. So they're going to go from the electrons that are moving to where they're going. And then we're going to have the brackets around the resonance structures. And then we're going to have a resonance arrow that goes between the resonance structures. So here are two super important rules for arrow pushing. Number one, you never want to break a single bond. So here we show that the electrons are moving from this single bond over to this single bond. And you know a single bond is 2 electrons, and this arrow is showing that we're moving 2 electrons. So if we were to move both electrons of this bond, we are essentially breaking it, and that is not what we want to do. The next rule is that you never want to exceed an octet for a second row element. So in this example, we have this oxygen, and one lone pair from the oxygen is being pushed over to form a double bond. If we form that double bond, this carbon is now going to have 10 electrons in its orbital, and that is not what we want. We always want 8 electrons in the orbitals for second row elements and above. So formal charges in resonance structures, when we're moving electrons, a lot of times the formal charge is going to change because those lone pairs and double bonds are what gives them the formal charges. So in this example, if we move this lone pair to form a double bond right here, and then we move these pi electrons and push them over to the next carbon atom, this carbon that originally had the formal charge now has 4 valence electrons, and so it no longer has a charge. But then we moved electrons over to this carbon atom, and it now has an extra valence electron, which gives it a negative charge. So that's just something to pay attention to when you're pushing electrons, is to always make sure that you're moving the formal charges correctly with it. So now we're going to do some practice. I drew out a molecule and I went ahead and drew the arrows, and so I want you to pause the video and then see if you can draw the other resonance structure based on where these electrons are moving. So here's the answer. We can see that the lone pair on this oxygen is being pushed down to form a double bond, and then the pi electrons from this double bond are being pushed over to that carbon atom. And so make sure you focus on the charges. This oxygen had a negative charge, but once we push those arrows down to form the double bond, it now has 6 valence electrons like it once. And so now it does not have a formal charge. But this carbon atom that originally had 4 valence electrons, once you push those electrons over, it now has 1, 2, 3, 4, and then there is a hydrogen atom right here that's attached to it, and that makes it have 5 valence electrons, which gives it that negative charge.
I hope you found this video to be really helpful. The concepts and information presented in these videos will be true no matter what Organic Chemistry 1 class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are a currently enrolled Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online, or just drop in during any of our open business hours. For more information about our current services, please visit our website. Thank you.